All right, today we're going to pull back the curtain on something really cool, chemical indicators. These are the clever little substances that let us actually see the invisible world of acids and bases, turning what could be dull chemistry into a seriously colorful show. So picture this. You're in a lab, and in front of you are a bunch of beakers filled with clear, mysterious liquids. How do you figure out what's what? I mean, you can't just take a sip to find out, right? And that brings us to the number one most important rule in all of chemistry.
Yeah, you never, ever taste chemicals. It is totally forbidden and could be incredibly dangerous. So if our sense of taste is completely off the table, we need another way to figure out what these things are. We need some kind of chemical detector.
And that's exactly what a chemical indicator is. Think of it like a tiny chemical detective. Its whole job is to hunt for hydrogen ions. When it finds a lot of them, or not very many, it changes color, giving us a bright, clear, visual signal that tells us if we're looking at an acid or a base. But how does that color change actually happen? Is it magic? Well, not quite, but it is a beautiful piece of chemistry that's all based on a principle called chemical equilibrium. So an indicator molecule is always in this delicate balance, kind of like a chemical seesaw, between two different forms. Let's just call them HIN and IN-. Now, what tips the seesaw one way or the other is the amount of acid, those H+ ions, in the solution. If you add more acid, you push the balance to the left. If you add a base, it starts gobbling up those acid ions and the balance gets pulled over to the right. And here's the payoff. Each side of that seesaw has a different color. The HIN form, which takes over when things are acidic, has one color. But when a base is added, the balance shifts to the IN- form, which has a totally different color. And if you want to get technical, theories like the quinonoid theory suggest it's not just the color changing. The molecule's entire structure is actually rearranging itself. That's what we see with our own eyes. Pretty amazing. And you know what's wild? This brilliant chemistry isn't just something that happens in a lab. It's happening all around us, right in nature. In fact, people have been using plants as indicators for centuries. For instance, you've got Litmus, which comes from lichens. It gives us this awesome little memory trick. BAR, base turns acid's red paper to blue. Easy, right? Then there's stuff you might have at home, like turmeric, the beautiful China rose, and my personal favorite, red cabbage, which can create an entire spectrum of colors.
Speaking of turmeric, let me ask you this. Has this ever happened to you? You spill some curry on your shirt, you get that bright yellow stain, and when you go to wash it, it suddenly flashes this deep red color? What in the world is going on there?
Yep, that's a real-life indicator test. Most soaps are basic, or alkaline. So when the soap hits the turmeric, it reacts with the curcumin inside it, changing its color from yellow to that reddish-brown. You literally just did a chemistry experiment in your laundry basket. Now, as cool as natural indicators are, sometimes scientists need something a bit more precise, a bit more reliable. And that's where synthetic, or lab-made indicators come into the picture. Two of the most famous ones are phenolphthalein and methyl orange. Phenolphthalein has this incredible dramatic change where it goes from totally colorless to this stunning, vibrant pink the second a solution becomes basic. Methyl orange, on the other hand, is perfect for spotting strong acids, where it turns a sharp, unmistakable red-orange. So here's the key difference. While natural indicators are awesome for simple tests and cool demonstrations, synthetic ones give you that high precision and stability you absolutely need for professional lab work, especially for things like titrations. Okay, but what if you couldn't see the color change at all? What then? Well, chemistry has an incredibly clever and really inclusive solution for that, taking us beyond the world of sight entirely.
These are called olfactory indicators. Instead of changing color, they change their smell. And this isn't just a neat trick. It's a game-changing tool that makes chemistry accessible for students and scientists who are visually impaired.
It's fascinating how this works. You can easily detect the strong, familiar smell of, say, onion or vanilla in an acidic solution. But if you add a base, like sodium hydroxide, poof, the smell just vanishes. It's completely gone. So here, the signal is the absence of a smell. So we've got indicators we can see and indicators we can smell. The final piece of the puzzle for any chemist is knowing how to choose the right tool for the right job.
See, the key to using an indicator in a procedure called a titration is to match it to the reaction's equivalence point. That's the magic moment when the acid and base have perfectly neutralized each other. So for example, if you're mixing a weak acid with a strong base, that point is going to be slightly basic. That's why you'd pick an indicator like phenolphthalein. because its color change happens exactly in that basic pH range. It's all about matching.
Now, you don't need a professional lab with fancy glassware to see this stuff work. Let's bring the science right into your kitchen with a classic and really fun DIY experiment.
It's super simple. Just chop up some red cabbage and boil it until the water turns a deep purple color. That purple water, that's your indicator. Let it cool, strain it, and now the fun begins. Add a little acidic vinegar and watch it turn pink. Then try adding some basic baking soda solution, and you'll see it shift to blue or even green. You've just made your very own pH rainbow. And really, when you get right down to it, that's what this is all about. Indicators, whether they come from a cabbage or from a lab, are these amazing tools that let us translate the invisible language of chemistry into a vibrant, visible one that we can all see and understand.
So now you know the secret. The next time you see a weird color change happen out of nowhere, you'll know it's probably just a little bit of chemistry at play. The real question is, what other chemical secrets are waiting to be discovered right in your own home? Thanks for joining us.